concept of simple machines. I see here three of the simple machines we talked about. An inclined plane up here in the top left, a pulley system here in the lower right, on the right hand side, and then a lever system with an elephant and a mouse in the bottom portion there. So we're talking about uses and functionality and some of the math concepts behind these. So first off, simple machines help us by either decreasing the amount of force required to do a task, or increasing the distance the object will move, or by changing the direction of the force of the system. All three of those things may be a benefit to us. So the idea there being that we're going to accomplish something that we maybe couldn't have accomplished on our own by changing one of those three factors. So in the ideal case, the perfectly ideal case where there's no friction, no energy loss, all the work that we put into a machine is going to be equal to the work that we get out of it. So all the energy we put in here for work is also equal to the work that we get out of the machine. Another way of writing that is F in D in equals F out D out, or fin din equals fout dout, meaning that no energy is lost, there's no friction involved, there's no outside forces really influencing how our machine functions. Real world, of course, that's not going to be the case, but ideally, so this is an ideal machine here, ideally with no other forces acting, that's what we're going to end up with. So we can end up calculating what's called the ideal mechanical advantage. How much of a benefit do I get without energy loss to using my machine, or should I get without energy loss using my machine? And it's going to be real simple. It's going to be the ratio of the distances. The longer the distance is, the more of a benefit you're going to get in terms of the amount of force you have to apply, or how much the force will decrease that you have to apply to do a task. So the IMA, or ideal mechanical advantage, is the input distance divided by the output distance, which for, say, a ramp, your input distance will be on this side, the length of the ramp that you actually have to walk. That's what you did, you put that in. The output would be the fact that out of that, you got to go up in the air. So that's going to be your ratio of your distances. The input distance, how far you actually walked, output, what you got out of it. For a lever or a seesaw or anything like that, if you're pushing the side you push down on, would be the input side. The side that goes up and lifts something is going to be the output side. Okay? For a pulley, it's pretty simple. It's basically whatever force you're putting into it. It's going to be how far the pulley moves, or how far the string moves, versus how far the object goes up in the air. So that's the ideal world. Real world, we have friction. We have something taking away some of the energy that we put into it. Not every machine is perfect at converting work. Actually, no machines are. There's friction involved with almost everything we do. So we have what's also called the actual mechanical advantage. That's when you really test your machine. What is the real benefit? So, for instance, so that's going to be the ratio of the forces that we get out of the machine versus what we put into the machine. So the IMA will tell you how much your force should be multiplied by. The AMA will tell you how much your force was actually multiplied by. So if we go back a little bit here, we might say that this is 5 meter long ramp and 1 meter high. Well, that would be an IMA of 5 is what we'd be hoping to get out of that. Meaning that if we might have to lift an object up, that is 100 newtons, is the normal force we'd have to lift up. Using this ramp, we would only have to actually apply 20 newtons worth of force, ideally. Okay. Let's instead say that we tested it out and it took us 40 newtons worth of force to push it up the ramp. We know that it normally would have taken 100 newtons to lift something up in the air. That means that our AMA is going to be the output of our system, or 100 newtons, divided by how much force we put into the system, or 40 newtons, which means that we only got a benefit of 100 divided by 40 is 10 divided by 4, which is 2.5. Means we only got a benefit of 5, would be our AMA. So we are hoping for that benefit of 5 based on the distances. We only got a benefit of 2.5 when we really tested it out. So that tells me that there's a decent amount of energy loss in my machine. And our next step is kind of figuring out how much energy loss there is percentage-wise. So for this one here, we called our efficiency. So we're going to do that by finding the AMA over the IMA. One way you can think about this is kind of like a grade. You're going to take your score, the AMA, here, divided by the perfect score, the IMA. Kind of like how you would find your grade on a quiz. So we're going to do 2.5 was what we really got. We're hoping to get 5. So that tells me that my efficiency for this machine is only 50%. And that makes sense because we had to put in twice the amount of force that we were hoping to put in. So that tells you that 20 newtons worth of force was probably going to just overcome friction. So how can we test this out in a couple problems? Let's do it real quick. We have a 3-meter long lever here used to lift a 250 kilogram object. So this is 250 kilograms, which means has a downward force of 2,500 newtons, or lift up into the air. We're going to apply 800 newtons worth of force downwards, which will in turn apply 2,500 newtons worth of force upwards to lift our object. Okay. We have our fulcrum here. Oh, let's draw it on the right side though. The object is only a ½ meter from the fulcrum, and we're applying the force 2.5 meters from the fulcrum. We want to know the efficiency of the lever. So efficiency, again, is going to be the actual score for the machine divided by the ideal score for the machine times 100%. The AMA will be the ratio of the forces. So F out over F in. In this case, we got out 2,500 newtons worth of force. We lifted that object in the air. That is the output of my lever. We put in 800 newtons worth of force. So if we divide 2,500 by 800, we get 3.1. Now there are no units here. Okay. For AMA or IMA, they are purely a ratio, so there's no units there. So our actual advantage was only 3.1. The ideal advantage would be the ratio of the distances, because there's no friction involved. So the input side, which is d in over d out. The input side is the side we pushed on. That is 2.5 meters long. The output side is the side that lifted up. That was a ½ meter long. So 2.5 divided by 0.5 means we're hoping to get a benefit of 5 by using this simple machine. We didn't. We only got a benefit of 3.1. So to find the efficiency, we do 3.1 over 5.0 times 100 means that we were 62% efficient while using this machine. Okay. Again, we're looking at the ratio of what we really did versus what we were hoping to get based on the ideal situation. So that means that 38% of our energy was lost. Probably went into friction and heat. Another example problem. Person pushes a 35 kilogram box. So this weighs 350 newtons. Up a ramp that is 5 meters long. So this whole thing is 5 meters and 2 meters high. The actual force required was 210 newtons. So what is the efficiency? Again, efficiency is the actual advantage divided by what we're hoping to get, the AMA. The actual advantage is the output force over the input force. In this case, the output force is lifting the object up in the air, so 350 newtons. The input force is the fact we put in 210 newtons. So if we do 350 350 divided by 210 we get 1.7 as our AMA. The IMA is going to be the ratio of the distances, so D in over D out. So ideally, we are hoping with a distance of 5 and a height of 2 to get a benefit of 2.5. So we only got a benefit of 1.7. We're hoping to get a benefit of 2.5 times the amount of force we put in. So 1.7 divided by 2.5 tells me that my machine was 68% efficient. Again, meaning that 32% of the energy was lost due to friction or some other source. So not too complicated. Hopefully it makes a little bit of sense in terms of what we're trying to get at there. The last thing to check on, to give examples of pulleys really quickly. Pulleys, basically we're looking for every time a string is used to support the weight of the object, it's going to add 1 to the IMA. So we look at this first pulley system here. You have one string right there. Well, it's a different color, sorry. We have one string right there and another string right there. So we have 1, 2 points of contact, and we have 1, 2 strings that are both going upwards. So each one is going to add 1 to the IMA, so we get an IMA of 2. Going down, we're going to draw a line straight across, and every point of contact we're going to add 1 to the IMA. Unless that string is going down, it's not helping to support the weight. So we have 1 point of contact, 2 points of contact, but the one on the left is going down or being pulled down. So in this case, we only get an IMA of 1. If we go over here to the upper right, we draw a line straight across. We have 1 point of contact, 2 points of contact, 3, 4, 5 points of contact. But this last one won't count because it's being pulled downwards. So in this case, we have an IMA equal to IMA for this one is 4. The last one, we'll draw a line straight across. We get 1, 2, 3 points of 4 points of contact, but that one on the far right isn't going to count because it's being pulled down. So we have an IMA equal to 3. What does that mean? Just to be sure here, if this is a 100 Newton mass, here, let's do a different color. This is a 100 Newton mass. Let's pick blue because yellow is not showing up. 100 Newton mass, that means in this case we would only have to exert 50 Newtons worth of force to raise the object up in the air. If this was a 100 Newton object again, here the F would be 100 Newtons because the IMA is 1. The only benefit is direction. Here, if this was 100 Newtons, the F would only be 25 Newtons worth of force. And here, if it's 100 Newtons, now the F becomes 33 Newtons worth of force. The trade-off being when for those decreases in force, again, we're going to get an increase in distance. So hopefully this helps with some of the examples with pulleys and simple machines. And again, we'll go through some of the stuff tomorrow in class. Again, make sure you guys understand everything clearly.